तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We would like to continue with our analysis of the oscillator and related problems, but before I do that, let us do one more problem of a general potential where I would like to introduce the concept of a stable as well as an unstable fixed point or critical point in the same potential. So I am going to look at a potential where you have a maximum as well as a minimum, and you know the maximum is going to be an unstable equilibrium point and the minimum will be a stable equilibrium point, and the question is what kind of phase portrait you get when you have both these equilibrium points present in the same potential. So let us simply take an arbitrary shaped potential, here's V of x. I would like to have a minimum as well as a maximum, so perhaps something of this kind. So let us say you have a maximum and then a minimum and it goes off in this fashion, and of course this point here is an unstable point and this point here is a stable equilibrium point, and we would like to know what the phase portrait is going to look like. We do not really need to know the equation for this potential, the actual equation, in order to draw the phase portrait at least qualitatively, but let us see if we can do this. I mean, we can write a formula down for this V of x. The simplest formula would be, well, if it has got a simple minimum here, it is roughly parabolic in this region, so it is quadratic at that point. So let us say 1/2 ax squared, and then it goes off to plus infinity when x goes to plus infinity, minus infinity on this side, so you need an odd term, therefore the next logical term is a cubic term. So let us put plus 1/3 bx cubed, where a and b are positive. That would be a kind of simple formula for a potential with this qualitative shape, and the question is what happens to a particle moving in such a potential, and what does the phase trajectory look like. Well, let us draw the phase trajectory right here on this place itself. So here is x and here is the velocity v, and we have, as always in these conservative systems, 1/2 mv squared plus v of x equal to the energy of the system, and this real number E in this problem, as you can see, can take values from minus infinity to plus infinity because V of x does so. Now what do the phase trajectories look like? Well, it is evident from what we said yesterday that if the energy is sufficiently low, if this is your total energy, negative value, then the system cannot penetrate into this region at all and must be restricted to the region, the classically accessible region to the left of this point. And as you know, if you come all the way from minus infinity, you can go up till here, and then you can roll down, and the trajectory would perhaps look something like this. And that is about it, the full trajectory. As you increase the energy, you penetrate further and further to the right till, of course, this point here corresponding to the maximum of the potential, then you would have a trajectory which does this, asymptotically reaches that point or asymptotically flows away from that point, this direction. But at this critical value of the energy here, and let me call it E subscript s, s for separatrix because it is going to separate two different kinds of motion. It is also possible that you have an oscillatory motion in this region here, and of course if you start here, it is going to take you an awfully long time to fall down in this potential well, go up till here and then crawl back up here, because as you come back the restoring force goes to 0, and therefore it is going to take longer and longer to reach this point, and this would correspond to a trajectory which does this in this direction. At intermediate values of the energy, so this is for E less than 0, at an intermediate value of the energy, say between 0 and E sub s, there are two kinds of motion. You could have motion in this region, so there could be a trajectory which does this, but you could also have oscillatory motion in this region here, which would correspond to something like this. Oh, I made a mistake, I exaggerated this, because if you are here at this point, you could never go beyond that point. So it is clear that I need to draw this more carefully. Here, reach that point, and then you come back. So notice that for 0 less than E sub s, you have both unbounded motion here on the left hand side as well as periodic motion in this well, and the moment you reach E sub s, you have reached a separatrix, you have reached the end point here, a little greater energy, a little higher than E sub s would imply that you can actually potentially come down, come up all the way, cross this barrier, go all the way up till there, and then you fall down, because when you come back here you still have that much energy, so you zip past this point and you fall off here. That would mean that the trajectory does this, it comes here, goes all the way around to that point, and then flows off to infinity. And this is for E greater than E sub s, this trajectory. This thing here corresponds exactly to E sub s, as do these two trajectories, this trajectory as well as this trajectory. These two trajectories correspond to E sub s, precisely E sub s. So now the separatrix separates unbounded motion from another set of trajectories, one part of which could be unbounded and the other part would correspond to periodic motion. And it is clear from this figure that this set of trajectories, the separatrices, now comprises really three different trajectories, one of them asymptotically flowing in towards this unstable fixed point, the saddle point, the other one flowing away from it, and the third one starting there close to it and asymptotically tending back to it. Unlike the previous case where we had 4 asymptotes quite separate, here one of them has curved back on itself, and it starts off as part of an unstable direction here, and I will explain what I mean by an unstable direction. Things are flowing away from it, but then when it comes back here it flows towards it again, and it forms a kind of closed loop here asymptotically, because this point, these things never touch this point, as you can realize, and this kind of orbit is called a homoclinic orbit or a homoclinic cycle, and it is going to play a big role . So this is the qualitative phase portrait of this, for this potential. Of course you can justify this, you can solve the equations of motion and so on, but I want you to notice two things in particular. One of them is that on all these trajectories, when the vertical axis, when the horizontal axis is intersected, the trajectory appears to do so at right angles, and this is indeed so, because if you look at the equations of motion, you have x dot equal to v and v dot equal to minus 1 over m v prime of x. Those were the equations of motion, and therefore the slope of a phase trajectory given by dv over dx, you just divide one by the other, and this is equal to minus 1 over m v prime of x divided by v, and whenever it intersects the x axis, little v is 0, and therefore the intersection is at right angles, the slope is infinite unless v prime of x happens to vanish also. then of course the slope is indeterminate and you have to take a limit, and that is precisely what happens at these points. Notice that these are not at right angles, and the reason is at this point v prime of x is also 0, therefore you have to calculate the limit as you tend towards this point of what the slopes are, and typically they would not be at right angles. So these would not be intersecting at right angles, but all these other points here the intersection is actually at right angles except the separatrix trajectory. And again I would call this a center because there are small oscillations about it. On this, in this point I would call a hyperbolic point or a saddle point, because locally the whole thing looks like a set of hyperbolas around it. So here is a problem where you have a stable as well as an unstable point, and you can see, you can generalize this, you can have many more of these. We will look at some problems where you do. It is immediately obvious that in these simple problems the maximum must be followed by a minimum. You can't have two maxima of the curve without a minimum in between, and therefore stable and unstable equilibrium points must alternate. That is abundantly clear, because it is very difficult to see how you could draw a trajectory if you have two centers next to each other with no other singular point in between. It is not possible. So already this gives us some inkling of what a general situation would look like. Okay, having done this, let us now ask, we have looked at the case of two equilibrium points, one stable and another unstable in the same problem. Let us look at some more cases. Let us look at a case where we include dissipation. We have not done so far at all, and we will not for quite a while in the formal development, but we may as well look at it in a very simple example, the damped simple harmonic oscillator. So let us look at what happens if I take just an ordinary simple harmonic oscillator and I put damping in there or friction in the problem. What does this analysis do for us? Well, the damped harmonic oscillator, simple harmonic oscillator, looks like this. All of you know that the equation is going to be x double dot mx double dot force is equal to force times mass times the acceleration is equal to minus m omega squared x. Let me call the natural frequency of the oscillator omega naught in the absence of friction, just so that I keep the notation straight, and then I would like to include the effect of friction. I pretend that this oscillator is moving in a viscous fluid, for instance. There are many ways of modeling friction. For instance, dry friction, which would correspond to what happens to this object, says if I push on it, it is not going to move till a certain critical stress is reached, and then after this threshold it is going to start moving. But then in a fluid this is not the way friction operates. In a fluid the friction would be typically proportional to the velocity, instantaneous velocity, and directed opposite to it. It is like a particle moving in a person moving in a crowd. The faster you try to move in a crowd, the more you get buffeted from the front, and therefore you have a retarding force on you. This is exactly the way you have a force proportional to your velocity. The faster you try to go, the greater the retarding force, and therefore it is reasonable to assume in the simplest instance that this damping force is of the form minus m, and it is proportional to x dot itself. So let us write the constant of proportionality as gamma and put an x dot. I do this because I know that this quantity m cancels out, by the way, in this equation, and I know that this is length divided by time squared, and this is 1 over time squared here. So this ensures that gamma has dimensions of time inverse. So that is why I put the m in there. And now if I write this in the way we are used to, well, you know the solution to this equation. This is an ordinary second order differential equation. So x double dot plus gamma x dot plus omega naught squared x equal to 0. And this is not quite so trivial to solve as the simple harmonic oscillator, where the solutions were cos or sine omega naught t. What does the solution look like? It has got an exponential damping. There is a damping which is whose coefficient is proportional to gamma here. We could write the solution down, but you really need to know how big gamma is relative to omega naught. They both have dimensions of 1 over time, and you need to know which is bigger. If gamma exceeds a certain critical value, in this case it is going to be something like 2 omega naught, then we know that the damping dominates over the oscillations, whereas if omega naught is bigger than half gamma, then the situation is that of an underdamped oscillator. So we have 3 situations depending on whether underdamped, overdamped and a critically damped oscillator. We would like to analyze all of them in one shot. We would simply like to know what the qualitative behavior of the phase trajectories is. So let us do that. Let us rewrite this as x dot equal to v and v dot equal to minus omega naught squared x minus gamma v. Well, that is our set of, yes please. It does not need to have a mass dependence. I put this, there is some constant here multiplying the velocity. I extracted an m and called the rest of it gamma, so that this gamma has the dimensions of time inverse the same as omega naught, otherwise the algebra gets messy. So it is just for dimensional reasons without any loss of generality. We are not talking about more complicated questions like why should it be linear in the velocity, why not the square of the velocity or the cube of the velocity and so on. This is entirely possible, and in fact if you ask what the drag force is on an object moving in air like an airplane, then the drag force is proportional to the velocity only for sufficiently small velocities, and as the velocity increases it becomes highly non-linear, right. I mean it is a much more complicated problem. So if I plot for example the speed here versus f drag, what does this curve typically look like? Well, it starts off linearly but pretty soon becomes quadratic, higher powers and so on, and then increases very steeply, and then it comes down once you break the sonic barrier. So as soon as you hit the speed of sound, after that the drag force comes down dramatically, but before that it increases extremely rapidly. Well, that is a highly non-linear situation and we are not going to look at that. We are just going to look at this little region here where the damping is proportional to the velocity, the first power. So here is our set of equations, and I prefer to work with this set of equations for several reasons. One of them is that it is a set of first order differential equations as opposed to a second order differential equation, which is always harder to solve. And the advantage or the physical insight you get into a set of first order differential equations is that to specify a solution uniquely you need to specify initial conditions, that is it. I just have to tell you what x is and v is at t equal to 0. I do not have to tell you what v dot was and so on, etc., etc. Just have to tell you 2 initial conditions, 2 coupled linear equations, and the problem is straightforward to solve. So it looks a little formidable in this language. You would think that it is better to eliminate and write it in this form and then try to solve it, but it is actually easier to solve in this in this format, as we will see. But before we solve the equation, since we are lazy, we would like to ask in physical terms, what do I expect, what can I expect of this. So let me do that as part of a general framework. I would like to write the following. I would like to write x as xv. Let me just define a vector, a 2-dimensional object with components x and v. They have different physical dimensions, but I will take care of that, I will be careful, and I will call it underscore x. That is not a coordinate, that is a point in phase space in xv. And then this set of equations is nothing but saying d over dt x dot this side is equal to some 2 by 2 matrix acting on xv, and this 2 by 2 matrix, let me call it L, and it acts on x once again, and the matrix L is 0 1 minus omega naught squared minus gamma. So its advantage is when you have a set of coupled linear equations, differential or otherwise, to write everything down in a matrix form. Then of course it is very easy to solve such equations. So this equation looks very, very simple as it stands. And what is the formal solution of this equation? Well, suppose x was just a number, I mean it was just an ordinary quantity, not a matrix, not a column vector, then of course it would be e to the power Lt of this. So the same thing goes through when this is a constant matrix. There is no x dependence there, there is no t dependence there. So this implies that x of t is in fact equal to e to the Lt, but I have to impose initial conditions. I have to tell you what x of 0 is. So x of 0, v of 0 has to be given to you, has to be specified, and let me call this x of 0, x vector of 0 by definition. So where does x vector of 0 appear there? Should it be on the right hand side or the left hand side? It should be on the right hand side, because we would like to have a 2 by 2 matrix act on a column vector to give you another column vector. So we have to be careful, we have to write this thing here, because remember this is a column vector and that is a matrix, 2 by 2 matrix, so we have to be careful, we can't write it in the other order as you could for ordinary functions. Okay. So that is the formal solution. But now I ask you, what is the meaning of this e to the power LT? What is the meaning of exponential of a matrix? What does that mean?
E is an operator which operates on each element in the matrix.
I define this exponential by its power series. I define it by its power series, and since we are going to play around with these things, might as well have them properly defined. So e to the power LT, t is just a scalar parameter here running from 0 to infinity, is just a real number, but L is a 2 by 2 matrix, and the definition of this is equal to a power series. So what is the first term in the power series? The identity matrix plus, of course, as usual, L square T square over 2 factorial plus etc. all the way to infinity. So let us write this as summation n equal to 0 to infinity LT to the power n over n factorial. L to the power n is also a 2 by 2 matrix. Now of course we are faced with a apparently formidable task, which is to find all powers of L and then add them up and sum it, but you do not have to do that. But even before I do that, I need to know whether this series makes sense. Do you think it converges? After all, it is an infinite series. Do you think it converges? Well, let us go back. We have channel 2 here, so let us go back and ask, what is the definition of e to the power x? This is summation n equal to 0 to infinity x to the n over n factorial. Of course, when does it converge? For all values of x, all values or less than 1 in magnitude? All values of x. Of course it converges for all real values of x, all finite values, and the reason is x to the power n increases, like x is large, maybe it increases a million, then it increases like a million to the n, but n factorial in the denominator increases like n to the power n, faster than e power. So this dominates, and of course the series converges for all x. Now the right way to look at it is to ask, when does e to the power z converge, where z is a complex number? That is the way to look at power series, always as the argument is a complex number. When does that converge? For all z, infinite, infinite. Will it converge if z is infinite? No, of course not. So all finite z, converges all finite z. As long as the magnitude of z is finite everywhere in the complex plane, this series converges absolutely. It converges so well that I can differentiate it term by term, integrate it term by term, I can do all kinds of things to it. But now we are faced with a matrix, and I have to decide whether it converges or not. For the complex number, I just said the magnitude is less than infinity, that is fine, but what about a matrix? How do I measure the size of a matrix? One way to do this would be to look at its eigenvalues and ask for all, if its eigenvalues are all finite, this would certainly be true. The other way to look at it would be to define a size of this matrix, size for this matrix, called the norm of the matrix. We will not go into this technicality, but as long as, let me just state that as long as all the elements of L are finite, this converges, there is no problem at all. You are guaranteed that all the eigenvalues are finite and so on, and there is no difficulty. This is one of the important properties of the exponential series. It plays a very fundamental role in all of analysis, and in this case there is no difficulty with convergence. We can close our eyes and go ahead and do this. Of course the next job is to find this number. We have to find this quantity here and then sum it, but we are spared this problem because actually what happens finally is that, what would happen? I take this L, I raise it to all powers and I do this summation, and finally I get an answer which would depend on the eigenvalues ultimately. You could imagine for instance that I diagonalized this L by a similarity transformation. If I could do this, and we will come to when you can do this, if I could do this, so I take this matrix L and I apply a transformation on either side, yes, and it gets written in a diagonal form, so it becomes D, and the elements of the diagonal form are of course the two eigenvalues of L, which I call lambda 1 and lambda 2. If I could do this, then it is immediately clear that S L to the power n S inverse is equal to D to the power n, which is in fact lambda 1 to the n 0 0. So you immediately get this result, because I write this L squared for example as L S inverse S and then L again and so on. So this is immediately obvious, and in fact you go a little further and you discover that S e to the LT S inverse equal to e to the lambda 1 t 0 0 e to the lambda 2 t. You discover that any function of L, once you diagonalize it, becomes just a diagonal matrix with a corresponding function written in each of the diagonal elements. And then to find e to the LT itself, all you have to do is to undo this. So I put S inverse on this side and get rid of that, and I put an S on this side and get rid of that. And what is the final outcome? It says e to the power LT acting on x of 0 does not do anything very much. It says that both x of t and v of t are just linear combinations of e to the lambda 1 t and e to the lambda 2 t, some suitable linear combinations. So for example in general this would look like some a e to the lambda 1 t plus b e to the lambda 2 t. This would look like it would look like this, where the combinations, where the constants a b c d would depend on x of 0 and v of 0 and some numerical factors. But the time dependence after this whole rigmarole is essentially this thing here, and this is what you write down when you take the second order differential equation for x double dot plus something, and you say let us assume a trial solution of the form e to the lambda 1 t plus e to the lambda 2 t, and then you discover that lambda 1 lambda 2 are the eigenvalues of this matrix. It is exactly what we have done. So this kind of thing justifies that finally you are going to get this behavior, nothing more than that. There is one exception, there is one exception. When would this not be the solution? Pardon me? Well, okay, no, we will come to that, it is a separate good point. His point is you may not be able to diagonalize this matrix, but I do not need to do the diagonalization, I just need to find the eigenvalues of the matrix, and that I can do whether the matrix is diagonalized or not, can be diagonalized or not. If the eigenvalue is repeated, if you have just one eigenvalue, if lambda 2 is equal to lambda 1, then what do? What does the solution look like? Yes, the solution is no longer a linear combination of e to the lambda 1 t and e to the lambda 2 t, but it is a linear combination of e to the lambda t and t e to the lambda t. If L is a 3 by 3 matrix or an n by n matrix and an eigenvalue is repeated r times, then for that eigenvalue the linearly independent fundamental solutions are e to the lambda t, t e to the lambda t, t squared e to the lambda t over 2 factorial for good luck up to t to the r minus 1 over r minus 1 factorial e to the lambda t. Well, that is the general case. We will look at the case of repeated roots later on, nothing much happens, but this is what the thing looks like. I have a little puzzle here, and that is we started by saying I give you x of 0 and v of 0, and I end up with solutions which look like this, but there are 4 arbitrary constants here a, b, c, d, but I give you only 2 pieces of information. How am I going to determine 4 constants from 2 pieces of information?
Derivative of
I'd use the equations themselves. I'd use the equations themselves. The differential equations are also valid at t equal to 0. So I'd use the fact that x dot equal to v and v dot equal to minus omega naught squared x minus gamma v, and if I look at this set of equations at t equal to 0, at t equal to 0 x dot of 0 is of course v of 0, but v dot of 0 is given by this, and I plug in these into the solutions. So I take these equations, and from these 4 equations I can find out all 4 constants provided I use the differential equations themselves. We will look at examples. So there is no conflict here, this is sufficient, we can actually find all the constants of motion, and the solution looks like that. Now if the solution looks like that, what does the phase trajectories look like? That was our aim after all, our ambition was simply to draw the phase portrait. Now what does the phase trajectories look like? So I still need to solve that problem. Here is x, here is v, and we have a mess of this kind, and you really have to eliminate t before you can draw the phase trajectory, but in practice we can do this in a much more simple way. What would the phase trajectories look like? I think physically, and I say, look, I know that if this is an underdamped oscillator, then x of t as a function of t, x of t would start at some point and it would oscillate, and the oscillation amplitude would decrease to 0. If it is an overdamped oscillator, then here is t, here is x of t, it would start and damp off in this fashion, and if x of t oscillates about its central point with decreasing amplitude, so does v of t, it is after all the derivative, and if it monotonically decreases to 0 in the overdamped case, so does v of t. So this immediately suggests that in general, if I start at some point here, this thing would spiral in towards the origin. Unlike the old case where you had ellipses, you do not have conservation of energy in this problem, and the phase trajectories would simply be some kind of spirals in the underdamped case. And in the overdamped case, you would have something starting here and essentially going off asymptotically to 0 without really oscillating. In fact, it will not even change sign if it is overdamped, so it should really start off somewhere here and you would simply fall in this fashion. We need to determine when it is underdamped, when it is overdamped, for which we need to know the eigenvalues lambda 1 and lambda 2, and that is trivial to do. So let us do that. Our matrix L was 0 1 minus omega naught squared minus gamma. That implies that lambda times lambda plus gamma plus omega naught squared equal to 0. Now that is the secular equation, and the roots are lambda 1 comma 2 equal to minus gamma plus or minus square root of gamma squared minus 4 omega naught squared over 2, and if I am interested in the underdamped case, then this becomes an imaginary number, so let me write this as minus gamma over 2 plus or minus I times omega s, where omega s is square root of omega naught squared minus gamma squared over 4. Pull out the 2 and I define a shifted frequency omega sub s, which is omega naught squared minus 1/4 gamma squared, and taken the square root, provided omega naught is greater than gamma over 2. So this would correspond to underdamped, omega naught greater than gamma over 2, and this is overdamped. In fact, it is a monotonic decrease, so it will just do this. Overdamped, this will be omega naught less than. The critically damped case is omega naught exactly equal to gamma over 2, and that is the case we have looked at, we talked already about, where this quantity vanishes and you have lambda 1 and 2 each equal to gamma minus gamma over 2. Yeah. Why do you say that?
Because x dot is positive and
x dot is positive. Ah, okay. Okay, I did that carelessly. It would it would be a part of a spiral going in, okay, in some fashion, depends on the initial conditions. Okay. It is not very interesting to me at the moment because I know I can always go to the overdamped case by going back to this, by writing this, by going back to this formula, writing this. The point is that in both cases, in the overdamped as well as the underdamped case, the system is actually reaching a state of equilibrium at the origin finally, because in the underdamped case there is no doubt about it, this point, this part here, so e to the lambda 1 t and e to the lambda 2 t, they both go like e to the lambda minus gamma over 2 t, and then the exponential of e to the plus I omega st or minus I omega st, but that does not matter because these things are essentially cosines or sines of omega st, which are oscillatory functions. In the other case, but they are damped due to this. In the other case, one of the roots minus gamma minus this square root definitely damps out very fast, and the other root minus gamma plus this number, minus gamma dominates over that because it is bigger than the square root here, and therefore it still damps. So both the roots have damping, they are not explosive roots, they both damp down to 0. As we expect, we have friction, so whatever the oscillator does, wherever you start, eventually the oscillations die down and the thing goes to the equilibrium point at the origin. Whether it does so by oscillating across this point or whether it does so monotonically is a matter of detail, it is not important at this stage, but this is what the phase trajectory looks like. Now what is the lesson from this? Everything depends on this eigenvalue, on the eigenvalues of this matrix L, that controls everything. So once the real part of this eigenvalue, if it is a complex set of eigenvalues, once the real part is negative, you would have damping automatically. So this is a new kind of equilibrium point, it is not a center and it is not a saddle point, but it is something else towards which systems asymptotically tend, the system tends asymptotically, so we have to classify this. But before I do so, let me settle a small mathematical point here. I mentioned that you start with this L and it is finally the eigenvalues of L that make a difference, but to get to this point, to justify it, I said let us assume that L is diagonalizable. You have to understand that all matrices cannot be diagonalized by similarity transformations, only some of them can, but you do not need the diagonalization of this. Independent of that, this is what the solution looks like. Okay. But as an aside, when can you diagonalize a matrix? When can you diagonalize a matrix? Yeah, if the matrix is real symmetric, you are guaranteed you can diagonalize it. In fact, you can diagonalize it by an orthogonal transformation. But what is the general case? When can you diagonalize an n by n matrix? This is a problem in linear algebra, it has nothing to do with this course, but it is good to get. Yes, indeed, yes. So, well, here is a simple sufficiency condition, it is not necessary but a sufficiency condition. If you have a matrix A and its Hermitian conjugate A dagger, by that I mean take its complex conjugate and transpose, it is called the Hermitian conjugate of the matrix. If A commutes with A dagger, which means that A dagger equal to A dagger A, by the way this stands for complex conjugate transpose. The Hermitian conjugate of this matrix, if it commutes with its Hermitian conjugate, namely if A dagger is equal to A dagger A, it does not matter in which order you multiply it, this is called commutation. This is sufficient to ensure that you can diagonalize A by a similarity transformation. By that I mean you can find a matrix S such that SA S inverse is equal to the diagonal matrix. It is sufficient, it is not necessary. You would also like to have a sufficient and necessary condition. Well, you know that every matrix obeys a polynomial equation, its own characteristic equation. This is called the Cayley-Hamilton theorem. So if you write down determinant of lambda I minus A equal to 0, you get an algebraic equation whose solutions form the set of eigenvalues of the matrix A, and this equation looks like, in general, if this is an n by n matrix, it looks like lambda to the power n plus A1 lambda to the n minus 1 plus A2 lambda to the n minus 2 plus An equal to 0. That is the secular equation. In general, this is what it looks like, and the constants A1, A2, A3 are determined from the elements of the matrix A. Okay. And the Cayley-Hamilton theorem says that the matrix A itself satisfies this equation. In other words, you are guaranteed that A to the n plus A1 A to the n minus 1 plus An I equal to 0, and this is the Cayley The statement is every matrix satisfies its own characteristic equation. But of course there is nothing to stop the matrix from satisfying another algebraic equation, polynomial equation of a lower degree. This could well happen, that the matrix satisfies an equation of a degree lower than n, and the lowest such equation, polynomial equation, is called the minimal polynomial of this matrix. The lowest degree polynomial equation, that polynomial equal to 0, that is called the minimal polynomial, and a sufficient necessary and sufficient condition that A can be diagonalized by a similarity transformation is that the roots of the minimal polynomial should be simple roots. There are many ways of saying this. One of them has to do with the rank of the matrix, which was mentioned indirectly here, but this is the necessary and sufficient condition. We will try to use it a little later, but let me give you an example here. Suppose you have a matrix, n by n matrix, all of whose elements are 1 1 1 1, everything is 1, and that is an n by n matrix. What are the eigenvalues of this matrix? Zero is certainly an eigenvalue because the determinant of this matrix is obviously 0. What happens if you do this? This is just playing with this matrices, but what happens if you apply it to this column vector 1 1 1? What do you get? You get n times the same column vector, n times the same column vector, right? So won't you say n is an eigenvalue? N is an eigenvalue, and all the other eigenvalues are 0. Every other eigenvalue is 0, because if you took this matrix, its determinant is 0. If you took the first minor, that is also 0, so you hit one of these columns and rows, and the rest of it also has 0 determinant, and that keeps going till you hit this element itself, and that is not 0. So all the minors are 0, and therefore this matrix has 0 eigenvalues, n minus 1 of them, and the last one is n. So this matrix has lambda 1 equal to 0, lambda 2 equal to 0, lambda n minus 1 equal to 0, just one of them. So it is easy to write down the characteristic equation of this matrix. It is immediately obvious from here what the characteristic equation is. So it says a to the power n minus 1, a minus n. That is the characteristic equation of this matrix. It is an nth order polynomial equation, and it guarantees that n minus 1 roots are 0 and one root is n. Instead of a, you replace it by lambda, and that immediately follows. But this is not the minimal polynomial of this matrix. What is the minimal polynomial of this matrix? What is the lowest order equation that this matrix satisfies? What do you think is the lowest order equation? Well, it cannot be a linear equation because A is not equal to a constant. A is not the identity matrix. So it can't be alpha A plus beta I equal to 0, it can't be an equation of this kind. The quadratic, what happens if you square this matrix A? Na, A squared is Na, so we know that A squared minus. So the minimal polynomial is in fact a quadratic in this case. What are the roots of the minimal polynomial? 0 and n, 0 and n. Are they simple roots? Yes. So you are guaranteed this matrix can be diagonalized by a similarity transformation. You are absolutely guaranteed. Yeah. What are the roots of this equation? 0 and 0, that is a double root, it is a repeated root. When I say it is a simple root, I mean the root is not repeated, its multiplicity is 1. What about this matrix, 2 by 2 matrix? Can you diagonalize this by a similarity transformation, do you think? Well, you can easily see a dagger is going to have a 1 here and they do not commute with each other. These two do not commute, you write a dagger and you get one matrix, you write a dagger A, you get another matrix, so they do not commute with each other. So it does not satisfy the sufficiency condition, but of course it may not be necessary. Now the question is, do you think this matrix can be diagonalized by a similarity transformation at all? What are the eigenvalues of this matrix? It is 0 and 0 because any triangular matrix in which everything below the principal diagonal is zeros, the eigenvalues are the diagonal elements themselves, and that is true for either upper or lower triangular matrices. So the eigenvalues of this matrix are 0 and 0. The characteristic function therefore must be of the form a squared is equal to 0. So the square of this matrix is the null matrix. That is also the minimal polynomial because the matrix itself is not 0 nor the identity matrix, so it cannot satisfy a linear equation. The next equation it satisfies a quadratic equation, but that must be the characteristic equation because it is a 2 by 2 matrix, and that is a squared equal to 0, and the roots are not simple. So you are guaranteed this matrix cannot be diagonalized by a similarity transformation, but it does not stop you from finding the eigenvalues here and here. So the best you can do to any arbitrary matrix is not necessarily diagonalize it, but put it in what is called the Jordan normal form. So what you can do is to take this matrix, this huge matrix, and you can put it in blocks of different dimensionalities, etc. So you can have something here, you can have something here, you can have something here, and so on in diagonal form, and in each block corresponding to a given eigenvalue of some multiplicity you can bring it to the form lambda 1, lambda 1, lambda 1, a 1 here, a 1 here, 0, lambda 1, 1, etc., and then zeros everywhere. For instance, if this eigenvalue lambda 1 has multiplicity 3, it is possible finally to bring the matrix to a form where you have lambda 1s everywhere on the diagonal, an upper triangular matrix with 1s on this side here, and similarly for these other things. If it is a simple eigenvalue, then you just have a 1 by 1 matrix, a lambda 1 in that block. This is called the Jordan normal form, and that is the best you can do for an arbitrary matrix. You do not need to, you may not be able to diagonalize it at all. So much for linear algebra. We do not need all this, but it is useful to know. All we need there is the eigenvalues. Okay. Now that we have this example, let us go immediately and generalize this to a more general arbitrary case of a dynamical system, and I would like to now define a dynamical system in the following way. Many definitions and this is a little bit of a digression into more general mechanics than what we were really planning to do, but I would like to do this because it puts the thing in a proper framework. Okay. Now what have we learnt? We have looked at different kinds of equations for very simple systems, particles moving in a potential and so on. We discovered we can write these equations of motion, Newton's equations, in first order form. It is a set of first order differential equations, and we are interested in the qualitative behavior of these solutions, not the quantitative behavior of specific initial conditions and so on, but the qualitative behavior of the solutions as a whole. And we had, in the simplest examples, we found that you have stable equilibrium points, unstable equilibrium points, sometimes equilibrium points around which the trajectories move, and other cases where they tend to these equilibrium points, and yet other cases where they are repelled outwards. So I would like to generalize this, and I start by saying, independent of mechanics, let us assume that all our dynamical systems are defined by a set of variables varying continuously in time, and that time is a parameter, the arena in which these variables move, and we have a set of evolution equations. That is it, I do not make any further assumption. So I start by saying my system is defined by a set of variables x1, x2 up to xn, n of them. I do not care whether they are positions or velocities or momenta, I will not even care if they are actual mechanical objects, they could be very complicated objects, they could even be populations of species competing with each other. There could be all sorts of variables, temperature, pressure, whatever, I do not care. I have a set of variables which changes with time, each of them is a function of time, and I prescribe the way these variables change, and I argue by saying that I have a set of first order differential equations. First order because I assume that these are the only variables needed to specify the state of the system completely. And once I have that, as an article of faith, I start by saying let us assume that they obey a set of first order differential equations, so that specifying the initial conditions would tell me the future completely. What is the most general set of equations you could write down, right? x1 dot equal to something or the other on the right hand side. It could be some function, arbitrary function of x1, x2 up to xn. It could in fact change with time, so I could perhaps have t as well in general, and then x2 dot equal to some other function f, so let me call that an f1, I make this an f2, x1, x2, xn, possibly t as well, and I go down all the way and I have xn dot equal to f sub n of x1, x2, x sub n and t. To start with, yes, I could think of more horrible complications. I could think of a situation where this set of variables x is itself continuous. You can certainly think of that. I could think of x to be, say, the pressure field in this room, and if I assume it changes from point to point and from time to time, then of course you have a continuous set of equations, and what would you then have? What would you then have? We will come to that, that is a very interesting question, we will come to that in a minute, but for the moment I assume this is a discrete set of variables. The other assumption I have made is that I have assumed that they obey a set of first order differential equations. There could be problems where intrinsically you cannot find this set of equations, we are going to ignore that for a moment. I have also assumed that time is continuous. If I did not assume that, if I said I monitor the system every year or every month or every hour, then time itself could be a discrete variable, and then I have difference equations rather than differential equations. So I have not been that general, but I have been fairly general in this sense. Now of course I have said that it could depend on time itself, this means the system is not autonomous, the rules are changing as a function of time, but then I would like to say let us look at the simpler case where the rules do not change with time. I remove this explicit t dependence here. By the way, even if I have that t dependence, I can subsume it in an autonomous system as follows. I play a trick and I say, okay, let me define xn plus 1 to be equal to t, I add a dimension and define it in this fashion, and then of course I have xn plus 1 dot equal to 1. Well, that is a nice function, it is just 1 on the right hand side, and all these are replaced by xn plus 1. So what I have done is to take an n plus 1 dimensional non-autonomous system and replaced n dimensional autonomous system and replaced it with an n plus 1 dimensional non-autonomous system, get rid of the t in this form. The physics could be very different, of course we will not get into that for the moment. I will give an example as we go along. What I would like to point out at the moment is, because of this possibility, let us look at only autonomous systems. So I simply have this, and I play the usual trick. I call this a vector, a column vector with elements x1 to xn and f1 to fn, another column vector, and then this set of equations can be written very compactly as x dot equal to some vector valued function of x, but this f underscore stands for a column vector with elements f1, f2, f3 etc., and each element is a function of all the x's, and this is an n dimensional autonomous system. Okay. Now task is to try to analyze this. In general it is a formidable task, but life can become very simple if you make certain assumptions on f which are not always valid, and we would like to go beyond those assumptions. But what would be the simplest assumption I could make? Well, if this is linear, if these are all linear functions, if this is a linear function of all its arguments, then the problem becomes x dot equal to some L acting on x, and I write the solution down by saying it is e to the LT acting on x. So a linear system is very simple, very easy to do. But before I do even that, I would like to ask, do you think there is a hope of solving such an equation at all? Is this possible? The answer is no. The answer is no, because what would you do to solve it without using a matrix method? If this is non-linear, then even matrix methods would not be so simple to do. What you do naively is to say, whatever we did in the earlier case, if I have two equations for x dot and v dot, I eliminate v and write it as a second order differential equation in x. What would you do here? If I started eliminating, in principle you would say, let us get rid of xn, xn minus 1 etc., and write everything as a function of x1. What order of differential equation would that be? An nth order differential equation. Then you would have a problem of solving a very complicated nonlinear equation. Matters are made worse by the fact that there is no guarantee you can do this. There is no guarantee that in general you can eliminate all these variables and do this. If I started with an nth order differential equation in one variable, I can convert it to a set of n coupled first order differential equations by defining the higher derivatives to be new variables, but I can't go backwards. So the real problem is this, and you can't go backwards. So you are really stuck with this thing here, and the analysis of this is incredibly complicated. All sorts of possibilities exist, and in fact beyond the small values of n we really do not know what is possible. Very, very complicated things can happen, and extremely intricate things can happen. And the big discovery made actually long ago but codified maybe 25 or 30 years ago is that beyond n equal to 2 you already have unbelievable complications. You have the phenomenon of chaos after n equal to 2. Till 2 nothing happens, but once you have n equal to 3, 4, 5 etc., things can get really nasty, and they can get extremely nasty, so nasty that it is not computable anymore at all. So that is the big discovery, and that is why we now say that chaos in classical dynamics is generic. It is the rule rather than the exception, and all the things you study normally in classical mechanics are exceptions. The real system is really very, very complex, much more. Most systems are chaotic, but there is a method in the madness. We found lots of ways of handling this difficulty, and this is some of what I would like to communicate to you. But before I do that, even I would like to point out that there is no difficulty whatsoever once you give me nice functions F1, F2 etc., to putting this on a computer and solving the equations numerically. You can always do that, because you give me an initial point in this n dimensional phase space, I use this set of equations, you have given me x at some initial instant of time t equal to 0, at an infinitesimal instant delta t I use this differential equations to tell me what x is, and then from that point I use the next delta t and so on, and therefore once you give it to me here I find out what it's here, what it's here, what it's here, I join all these guys and I have my phase trajectory. So it's really solved in that sense. You have to be very careful, you may need a very fine time step. If the function is very nonlinear you may need a very fine time step, but in principle you can do this always. So solvability is not the issue, you can always solve it for some initial conditions, for specific initial conditions. We have a much more ambitious program, we want to find out what is the solution for long times, arbitrarily long times. So we would like to know, if I start here, what happens after a million years, and this is of interest to me because I could be talking about the solar system, and it's of deep interest to know what happens at long times, and maybe it is not possible to integrate, you may not have enough computing power or time to integrate. In fact what happens is errors multiply exponentially and you cannot compute. So this is really the difficulty in dynamical system, but in principle solvability per se is not the issue at all, you can always solve these equations locally at any point. On the other hand you can't write the solution down explicitly, so that is integrability, you can't integrate this, and that is the harder problem. But I want to emphasize this again, solvability does not imply integrability. By integrable I mean I should be able to write these solutions down as explicit formulas, as functions of time. So I can put t equal to 20 million years and get what happens 20 million years from now. It is not clear whether you can do this, and it is not just hypothetical in terms of millions of years, because it is a matter of scale. For the solar system it could be millions of years or billions of years, but for elementary particles like particles inside an accelerator which are moving at speeds comparable to the speed of light, it could be 1 second, and that is equivalent to millions of years for the solar system. So if within 1 second things become unpredictable, that is very bad news, and therefore you would like to know how to handle such systems, and there is no question of saying I would like to know what happens at long times, that is going to be the phrase I use. I would like to see if I can handle this kind of thing at long times. Let me start at this point tomorrow and show you what this solvability means and why it is not integrable in general. After that we will go back to the general set of equations and be a little less ambitious and start with 2 by 2 systems, analyze that completely, and then see what we can say for n by n cases. And in fact once one understands that in that framework, the rest of mechanics, the rest of classical dynamics is actually special cases, various interesting special cases. So I would rather do that and introduce the Lagrangian and the Hamiltonian and so on as special kinds of dynamical systems which are part of this more general framework here, because it is useful to know this kind of thing, especially the question of stability. We would like to especially understand this, because I have in mind situations where as engineers you would face not just mechanical systems, not just electrical systems, you could have electromechanical chemical systems. Some of your variables could be machine parameters, some of the variables could be positions of rigid objects, orientations and so on, yet others could be concentrations of chemical species. We would like to be able to have a framework where you can handle all these situations in one shot. So let me stop here and we will take that up.